Morning, everyone. Thank you for joining us. I'm pleased to introduce Colin McCabe from Compliant. Colin is a software engineer who previously worked on Hadoop distributed file system, the Ceph file system, and H3 distributed system. He currently works for Compliant on improving for the performance, scalability, and general awesomeness of Kafka. Colin studied computer science and computer engineering at Carnegie Mellon University, and he enjoys home brewing and scuba diving. He will be presenting a talk titled Building Microservices with Apache Kafka. Please join me in welcoming him.
Thanks very much for the intro. Let me just set up my clock here. Okay. So, yeah, I'm here to talk today about building microservices with Kafka. And along the way, we're going to talk a little bit about like what a microservice is, why you would want one, how Kafka makes everything work better in this context. So yeah, we had the intro, so I won't recap. I just like to say that I work for Confluent, and we are the Kafka company, so we're doing lots of cool stuff with Kafka in many different dimensions. Hosted Kafka, new features for Kafka, all that stuff. So today I'm going to talk a little bit, I'm going to give a little example of a network service, a newsfeed reader, to make things a little more concrete, because I think that that often helps explain. And hopefully this will help us sort of understand why we would want microservices. You know, why are they cool? Besides being a buzzword, of course. And also, like, why is Kafka good for microservices? So this example should help with that. After that, I'll talk a little bit more about the background of Kafka, where it came from, where it's going, a little bit about how it works and what the concepts are there. We'll talk a little bit more about how some of those concepts make microservices more scalable, more decoupled, and better. And along the way, we'll touch on two Kafka APIs, the Kafka Connect API and the Kafka Streams API, which are very important in this context. And after that, we'll wrap up and talk a little bit about future work. So let's talk about a simple newsfeed application. Maybe one of those infamous reader applications that allows you to find some RSS articles and gives you a daily newsfeed of what's going on your favorite news sources. And presumably it will use machine learning to try to figure out what you really like. And it will have features like emailing you articles that you like, if that's what you choose. It'll have features like sharing articles. And of course, it'll be a network service, which is provided over the web. So we talked to our engineers, and their first try was a monolithic service, which is basically everything in the same process on a single node. So our product managers identified three major requirements here. I know it would never only be three, but bear with me here. One of them is that we want this service to be able to send emails to people who request those emails, so your news story of the day. The other is we want to export this data to HDFS, so we can start processing it with Hadoop and get all of our Hadoop-y goodness there. And the third one is we want to be able to track metrics about this service, like how many users are using the service in each different region, as well as metrics that pertain to the operation of the service itself, like what's the load on this server and stuff like that. So our single process does work, you know, it gets off the ground, but there's a bunch of problems with it that we discover down the line. One of them is that the emailer keeps crashing, and when it crashes, it takes down the whole service. So 404, nothing returned, bad user experience there. The other is that our metrics connector is using a lot of memory, and that's causing out of memories in this process as well. whenever we upgrade Hadoop, we want to upgrade the Hadoop connector, but that involves taking down the whole service. And then, of course, we're unavailable and people are sad. So in general, the single process works, but we just don't really like it. We feel like there's limitations on the scalability of it, and there's limitations on how decoupled things are. Things are not decoupled at all in this architecture. So our second try is to use microservices with the REST API between them. So what I mean by that is that the front end will receive a user request and will then make REST requests to different microservices that we've set up. For example, we might have an emailer service which has a queue of emails that it needs to send. We might have an HDFS connector service which has a queue of things it wants to send to HDFS. We have a metrics connector that does stuff with Grafana or whatever metric service we have. It'll do that export. So this is actually a lot better because now we can upgrade HDFS and also upgrade its client without bringing down the front end, which is really nice for our users. Now if the emailer crashes, the front end doesn't crash, so that's pretty good. And similarly, if we have an out-of-memory error in metrics, well, that really only affects metrics. It doesn't affect everything else. Or does it? So the problem is that because we're making these REST requests, we have to wait for them to complete. And that turns out to be a problem in some contexts. For example, like if the emailer is having a really high latency for accepting new requests, then that's going to be reflected in slowness in the front end, because the front end is waiting for this thing to actually say, yes, I finished the REST request. Or at least it's waiting for it to finish the REST request itself. And so as a consequence, we're kind of coupling the latency behavior of our front end to the back end directly. And so if anything in the back end is slow, then the front end is slow. As we add more and more services, that's going to be less and less scalable, right? Because just as a matter of basic probability, the probability that one of these services is going to be slow being reflected in the probability of the front end being slow is not a good thing. And of course, you know, we also have the issue that, let's say that the HDFS connector is down for an upgrade. Well, what happens to that data that was going to be sent to HDFS? If the front end isn't storing it, then that data is gone, right? So we lost it. So using a synchronous API like REST isn't really kind of what we want here. So our third try is to use Kafka here. And the way that we would do this is the front end would actually create messages, which it then sends into Kafka, into the Kafka message brokers. And then these services, the emailer, the metric service, and the HDFS connector become consumers of Kafka. And that solves the problems we just discussed. Because if the emailer is being slow, that doesn't block the front end putting messages into Kafka. Obviously, if we take down the HDFS connector for a little bit, that's okay. The messages that are in Kafka are not lost. And if we bring up the HDFS connector later, those messages will be moved into HDFS properly, because we maintain the offsets of all the consumers. So we know how much each consumer is consumed in Kafka, and we track that information in Kafka. So this architecture, so basically let's go over what the themes were here, right? So decoupling was a huge theme here, and scalability was the other huge theme. When we started with everything in one big application, we had no decoupling. Everybody was sort of everybody else's immediate neighbor, and anyone crashes, everyone crashes. Anyone's slow, everyone's slow. When we moved to having a synchronous API, such as REST, you could also substitute gRPC or Corba or any synchronous API you want in this diagram, there would be no difference. But when you have the synchronous API, you have to wait. And sure, you can parallelize some of these calls, I'm sure, but ultimately, you're going to be waiting for the maximum of the longest call to be done. And you really don't want to block the front end on what the back end is doing. So when we moved to Kafka, we actually found that we had full decoupling, because the front end could continue putting messages in the queue, even if the back end was having latency spikes, or we took some things offline for a while. Because ultimately, it was just boiled down to putting messages in the queue. And similarly, we could tell a similar story about improving scalability. When you have everything on one node, you know, I hope I don't need to convince you that that's not very scalable. Having a single process on one node. Now, when you have REST, yes, you can have multiple nodes and one node per service. But when you have Kafka, you can actually scale even beyond that. And we'll talk a little bit more about that later, how that would work. So this is a good time to talk a little bit more about what Kafka is. So Kafka is a distributed streaming platform, and it was built at LinkedIn around 2010. It has a ton of clients in every platform, so Java, Scala, C, C++. So if your project uses Go or C#, don't worry, we've got you covered. It's more than just Java, which is not necessarily true of all big data technologies. So Kafka's popularity has really exploded over time. You can see that the search terms, the number of Google searches that we've gotten for Apache Kafka has really grown since 2012. And the adoption has really grown too. So we have adoption in financial services, consumer technology, entertainment, telecom. And you can see a lot more of these logos that I didn't have space to fit here if you go to the Powered by Kafka page on the Apache Kafka website. So Kafka has 4 APIs. The producer API, the consumer API, the connector API, and the stream processor API. And the 10,000-foot view is basically that the Kafka cluster is made up of brokers and also Zookeeper. So you have multiple brokers in Kafka, and you have Zookeeper set up, and that's your Kafka cluster. And then you have clients that are sort of around the edges that are connecting to that cluster. So the first API, I guess, to cover is like the producer and consumer API. And this is sort of just what you would think. Producers write messages, and consumers read messages. And messages are comprised of a key and a value. And there are some other fields in there, too, that we've added over time, such as timestamp. But in general, the key and the value are the most important thing about messages. Another thing that I think it's important to note here is that you can have multiple producers and multiple consumers in Kafka for the same topics. And that isn't necessarily true for all queuing systems. But certainly for Kafka, multi-producer and multi-consumer all the way. And as I said earlier, each consumer has its own offset. So, sorry. Like I said earlier, you can actually have consumers consuming from different parts of the topic. So let's talk about where we're putting these messages. So messages go into topics. And a topic is kind of a collection of related stuff. So it's something with a theme. And producers will be producing to the end of the topic, and consumers will be consuming from whatever part of the topic they want. Generally, they'll be following along with the topic, but of course they could go back in time if they want to as well. So for example, just to tie that back into our newsreader example, what if we had a message which basically said, hey, there's been a view of this news story by this user at this time, and this is the story ID. So that might be one message in the views topic. And then the front end would be producing these messages, and all the back-end processes could be consuming these messages. So Kafka is durable. And what do I mean by durable? Well, I mean the most obvious meaning is just that we persist stuff to disk, which again, not every queuing system will do. And that actually means that it's a lot more safe to put your data in Kafka than some other systems that are just in memory. I mean, I'm not saying in-memory systems are bad, they have their uses, but I wouldn't use them for this. Kafka is also durable in the sense that we persist data to multiple brokers. So if we lose one broker, we don't lose all of the data in the topic. Log retention is configurable. And what I mean by that is that Kafka will delete messages that are too old if that's what you want. It'll keep them around if that's what you want. We have retention by both time and size. So again, relating it to our example, maybe we have the HDFS connector reading from this part of the topic, we have the metrics connector reading from that part of the topic. They can both read from the topic and do what they want with the views information that we have there. So Kafka actually helps you scale. And it's scalable in the sense that you can have multiple producers and consumers, which allows you to easily add new microservices. And it's scalable in other ways too. But talking about the multi-producer, multi-consumer thing for a moment, when we had the REST API, we actually had to change the front end each time we added a new backend service, because now you have to make a new call, right? And that's going to be recompile, redeploy, whatever it is. Maybe you're using node.js and you don't recompile. But in any case, you're certainly doing a redeployment. With Kafka, you don't have to, because when the data is in the topic, you can add a new consumer on the topic later. There's no coupling between that. And of course, it's scalable in the sense that you can add more Kafka brokers, so if you need more topics, if you need more messages, you can scale horizontally. So topics have partitions in them, and partitions are basically a grouping for messages in a topic. So each partition of a topic is on a different set of servers. Like for example, maybe our topic with views has 3 partitions. One partition is on servers 1 and 2, the other's on servers 2 and 3, the other's on servers 3 and 1, or something like that. So the general idea is this is kind of like a shard for the topic. And having these partitions helps us scale on the consumer side. Because assuming that these cylinders are partitions, Kafka will map partitions to consumers in sort of the most parsimonious way it can do so. So in this example, we have 4 partitions and 3 consumers. So Kafka takes a look at that and says, well, we'll give one consumer 2 partitions and everyone else gets 1. And what that means is that, first of all, we can run multiple emailer services very easily, because we simply spin up a new service, it consumes from Kafka. Whereas earlier with the REST API, we could not do that. We were limited to 1 emailer service, because we're only making a call to we're only making a REST call to 1 node in that case. But in this case, Kafka allows us to scale out with our consumers as well as Kafka itself. And bear in mind that these partitions are going to be on different sets of servers. So we're actually scaling not only sort of in a logical way, but also physically on the network. We're talking to different servers, and we're using hardware resources effectively. Now, what happens if one of our emailers crashes, like we said, has a tendency to happen? I don't know why. I didn't write that code. But in that case, Kafka can actually rebalance the partitions so that the partitions are distributed among the existing consumers. So again, this is just a sort of way you can get elastic scalability with Kafka. And you could say the same thing if you added more emailers as well. We would then do a rebalance, and perhaps we would no longer have an emailer handling 2 partitions. We would simply balance it so everybody got 1. And the concept that you need to do this is this consumer group concept. So you set up a consumer group, which then Kafka will do this balancing for you in it. So we talked a little bit earlier about connecting to external services, which is a great thing to do and one of our design requirements. So we want to send stuff to HDFS and to Hadoop. So normally you might think, well, we just kind of have to write that code. But actually that's not true, because Kafka has the Kafka Connect API, which already has that code written for you. So we already have code that will take stuff in a Kafka topic and export it to HDFS. And the Kafka Connect API has a lot of great stuff like this, where you don't need to write the code because the code is already there. There's already basically a pre-written service that does this, that can be configured. So in general, the Kafka Connect API has these concepts of connectors, which are responsible for copying data between Kafka and an external system. And some of the external systems we have are Hadoop. We also have RDBMS, lots of other stuff. This can also be done as an import. For example, you could import changes to your RDBMS to Kafka. So this is kind of the functionality of log shipping that you might see in the RDBMS world. And it's actually a really cool functionality for, again, adding decoupling to your architecture, because you can take something that was formerly trapped in one place and actually replicate it and do what you need to do in that other place. You can take stuff from SQL to Hadoop, you can go the reverse direction, and so on. So again, in our example, we could just plug that in, and now our HDFS connector is done, and we don't need to write that service ourselves. So we talked a little bit about the first three APIs of Kafka: producer, consumer, connector API. What about the stream processor API? In some ways, this is actually an even more interesting API because it allows you to process streams of data in real time. And of course, you have all the fault tolerance and you have all the scalability of Kafka when you do this. So let's take a little example. In our newsreader, we have some clicks coming in. So maybe we have a clicks topic that says Alice clicked 13 times in the last 2 minutes or something. And we have a locations topic which says Alice is in Europe, Bob is in the US. Now we want to actually create this clicks per location table. So this is a classic join operation in the RDBMS world. We're basically taking the data in one table and joining it with another. So obviously we have to, we have to pull out a huge framework, right? Well, actually not. We can do this with Kafka streaming without deploying any additional daemons. We can just use Kafka itself. So the Kafka Streams API allows you to set up these streaming computations where the inputs and the outputs are Kafka streams. And you get all the fault tolerance, the rebalancing, and the scalability provided by Kafka. The two main concepts that we have in Kafka Streams are the K-stream concept, which is a stream of values coming in. So it's an infinite data source. And the K-table concept, which is basically the latest value for each key in a stream. So one way of looking at this is that a stream is a changelog for a table. And a table is just the latest value of anything in a stream. So if we wanted to do this joining in K-streams, the first thing we might do is we set up this user click stream, which has the data coming in, like we talked about earlier. It has the clicks from Alice. So maybe it has a key of Alice and a value of 13. And then we join it with the user regions table, which is a K table, again, the latest value of this stream. And the user regions table basically maps users to regions of the world. Then we actually do a left join on these two, on the K stream and the K table. And finally we do a reduce, and now we have the output of this in our clicks per region topic. So we can simply read the output from this clicks per region topic. And it's configurable how often that output will appear and what triggers it to appear on that topic. So if we wanted to look at where this would fit into our architecture, we could use that for our metrics system, right? So we could get the metrics that we want to do. We want to get this metric of how many clicks per region we had. Well, we can actually do that with Kafka Streams. Again, our product manager said you have to connect to Hadoop. Well, we can do that with Kafka Connect. And we don't actually have to write that service ourselves. Maybe we need to have more emailers. Maybe we need to scale out all these services. Well, again, we can do that with the load balancing and scalability that Kafka has. And by the way, this scalability is not limited only to this component, of course. Connect has multiple worker processes sometimes. We could certainly have many worker processes in streams. And of course, finally, we've finally decoupled the front end and the back end. So as the organization grows and as people add more features, especially, we don't have to re-architect the system. We don't have to have a bunch of REST APIs that we keep adding. or other synchronous APIs. The front end doesn't really need to care necessarily about how many services we have running on the back end. As long as we have a clear model for our data, and as long as we're exporting the right data, we can actually work with it. So that's kind of my wrap up for how Kafka can help you scale this service. Let me talk a little bit about some of the new stuff we're doing in Kafka. One of the new things we're doing is exactly once semantics. So exactly once semantics are basically delivering end-to-end exactly once. So in other words, if you K-streams should process each message only once. Kafka Connect should export each message exactly once. Obviously, because this is a distributed system, it's pretty tricky to do that because you have stuff like failures and you have stuff like messages getting lost on the network. Unfortunately, I don't have time to explain that in 5 minutes, but there's a ton of blog articles about it. And so definitely follow up on that if you're interested. Another new thing we have in Kafka 0.11 is we have some pretty nifty performance improvements in both the producer and the consumer. Up to 20% in the producer, up to 50% in the consumer. This was a side effect of some of the optimization work that we did as part of implementing exactly once. On the Kafka Connect side, we have some pretty good class path isolation now, which solves a long-standing problem that we had with stuff. I want to say jars leaking in from other parts of the class path. But anyway, class path isolation is a really great feature, so check it out. So anyway, the conclusion here is that Kafka is really great for microservices because of the loose coupling, because of the deployability, and because you can actually scale with this stuff. It's really a useful building block. And I actually really like the concept of building blocks rather than necessarily frameworks, because building blocks let you use what you want to use. Frameworks don't always do that. Kafka is reliable. We didn't really talk a lot about the fault tolerance of Kafka in this talk, but we do spend a lot of time on that, as do most big data projects. So you can leverage this reliability to get the reliability in your application. And certainly Kafka Connect is really important for people who want to build real-world apps without writing a ton of code. And Kafka Streams is actually gaining a lot of traction as well. And it's a really interesting way to do the kind of streaming computation that's getting so important lately. So if you like this talk, there's actually a lot more that we've written. Especially Ben Stopford has written a lot of stuff about microservices. He's got a lot of blogs and talks that go into a lot more detail than I could here about how to model your data, what are some good patterns and anti-patterns in microservices, and using Kafka. So definitely check that out if you're interested. So yeah, check out our download page where we offer obviously Apache Kafka, but also all the other stuff that we have in our platform. And of course our careers page if you're interested. And finally, Kafka Summit is coming up, so don't miss it. I'm going to take some questions now if we have any time left. Do we have any time? Okay, sure. So it's going to have to be a little quick, but questions?
Yeah, I have a question. Is streaming in Kafka Stream batch type or proper stream, true streaming?
So the question is streaming in Kafka Streaming batch type or proper streaming? I would say that the approach that Kafka Streams uses is not really a micro-batch approach as described by like Spark streaming. There are cases where there is a certain measure of deferred computation, like we only output the results of a join every so often, for example. So it might be hard to give an answer to that question without defining the terms a little more clearly. But in general, you know, we're not running a MapReduce job periodically. I think your intuition should be that we're very close to being true streaming. And if you configure it in a certain way, then yeah, we'll do completely real-time streaming. So the short answer is yes. Long answer, it's complicated. Yeah.
That sounds like a marriage proposal.
Ouch.
It kind of is. That was awesome.
What does it mean for a consumer to have assigned more than one partition? Is that only about durability and like availability, or
Well,
is it about performance?
So the question is, what does it mean for a consumer to be assigned more than one partition?
Yeah.
And the answer to that is just that the consumer will consume from multiple partitions. So your intuition here should be Kafka's trying to load balance this output stream, right? And it's going to load balance it the best it can. If it can do one-to-one, so one partition per consumer, then it will. If it can't, then it won't. So it really just simply is that you're consuming from multiple partitions. And there's actually a lot more complexity here. There's more configuration you can do. Like, for example, you can round robin between partitions, or you can do something a little more clever. So there's a lot of configurability there, but I think most people stick with a sort of more basic round robin in that case. Yeah. Oh, the question is, how do I compare Spark Stream with Kafka Streams? Wow, that's a tough one. You know, I think both of them started in a very different place, right? So Spark started with what Spark had, which was basically a better MapReduce, RDDs, resilient distributed data sets. It started with its concepts of distributing things across executors, owning the whole computation. And Kafka started with this concept of clients are libraries. So clients are pretty lightweight. Clients will interact with Kafka, but they're not, like your application can do other things. We're not saying, hey, run this giant framework. So they're very different in that sense, that Spark Streaming is a library rather than a framework. I think they're also a little different in the sense that we do not do micro batches in the same way that Spark Streaming does, which is sort of an architectural difference. I think that, yeah, doing a deep dive on the architecture is probably out of scope right now. But we have a lot more stuff on the blog, and maybe I could give you a link to something that does a little more detailed comparison. Anyway, thanks guys. I don't know if we have any more time. I think we're almost out. Unless there's maybe one more question. All right.
When are you going to extend the stream and connect to Python?
To ByteStream?
To Python.
Python. That's a good question. So the question is, when are we going to extend the stream and connect APIs to Python? So there is a project in the works to try to do a native, or rather C or C++ streams implementation. And if we did that, then we could presumably extend that to Python. I'm not going to commit to a date here, though, because right now we're kind of trying to focus on building out the feature set that we want for streams. So I don't think we have a definite hard deadline for that, but there are definitely people working on it in the community. And if you're interested, you can check out those efforts and maybe even get involved. So, all right, thanks guys.